welcome to this, I think, last bite-sized session of today. So today I wanted to talk about the AWS Lambda or serverless functions and improvements when we talk about Java. I initially, when I submitted this talk, I said 10 performance improvements, but I think it has grown until 14, and while I was in the car on the way here, I thought of another one, but I think I'm running already a bit short on time, so I'm going to make it very, very quick. Very quick, my name is Jeroen Reijn. I do a lot with Java and AWS, and I do a lot with serverless. I'll keep it at that. Serverless functions. Anybody in the room who's using that? Can I see some hands? Oh, okay, that's like a third. Very good. So then I hope I can teach, for all the rest, I can teach you some stuff or either make you enthusiastic to start working with serverless. When you start looking at serverless functions or AWS or Google Cloud Functions, usually what you see on the internet is that people have a bit of a resent, like Java is very slow. But is Java really slow? In my experience, it's not slow. It's very fast, especially once the JVM gets running and is optimizing, it gets faster and faster. And if you start reading a bit about it, usually it's this one word or these two words called cold start. And that's sort of what most people are afraid of when they talk about serverless functions. Like AWS Lambda functions or Google Cloud Functions, they can scale up really quickly. And if your process or your application or your function is really slow in the initial phase, it will be bad for user experience. But cold starts in general, if you read about it and read what the cloud vendors say about it, it happens in 1% of the entire number of requests that you're trying to push through or trying to process the events through when you use serverless functions. For those of you who do not know what is a cold start, if you start a serverless function, in essence what happens is the runtime environment will download your code, because it's the only thing that you deploy when you work with serverless environments. It starts like an execution environment and a bit of context. Then it tries to initialize the code and then actually performs your business logic. So in this diagram on the left, the blue boxes, that's sort of what the cold start is, and usually also part of your initialization part of your function. And once it gets going, it gets really quickly. So when do these cold starts happen? Especially during bursts. So normally if your serverless function has been started and it's running, it's fine, the JVM is really quick, it's really fast. But if you get a burst, so you get, in this example, you get 6 concurrent requests, and there was no function at the time, because it scales from 0 up until a very big number. Then the serverless environment, like AWS Lambda, notices that there's no current warm environment available. So what does it do? It will start multiple environments at the same time, which, of course, if you have a very slow piece of Java, can take quite some time. If the requests come gradually, one after another, it's less of a problem, because you will have 2 cold starts, and you will have a lot of warm invocations, which are really quick. That's about cold starts. So since I only have a couple of minutes, what can we do to prevent these, and what can we do to optimize these serverless functions? The very quick win usually is just give it more memory. In most of these serverless environments, more memory equals more CPUs equals more performance. Especially with the JVM, can be very slow initially, but once it gets going, like I mentioned, it can become really quick. So more CPUs can really improve the startup process. And for instance, if you look at AWS Lambda, there's a range of memory that you can provide and the amount of virtual CPUs that your function will get to improve this performance. So more memory equals more CPUs. And if you've ever worked with AWS CDK, for instance, it's really simple, just configure it. So this is a very simple example of a Lambda function with the class and the memory size. Now you have memory and CPU, and the interesting part is what is really working and what's the optimum value for your memory setting. So there's this very nice little tool called Lambda Power Tuner, and you can give it your function and you give it a set of configurations. It will provide different memory settings, and it will try to find the sweet spot for your function. So that was one to improve your performance. Just give it more memory equals more CPU. Second one, static initialization. So static initialization means that if you look at this example function, and you look at this particular piece of code, what we're doing here is we're setting up a client that wants to connect with the DynamoDB database. And if you execute this same function multiple times, it will again and again initialize this client, which usually has a lot of overhead, needs to set up like a TCP connection to the service. So very first good step is for like resource-intensive operations, put them out, it's very simple, put them outside of your handler function. That will cause like the initial invocation and the start of the function to actually execute this. And when the function actually starts to serve like traffic, it will be done and it will only perform the logic itself. Very simple. By doing this, you can already like shave off a couple of 100 milliseconds for a function. Third, use lightweight dependencies. And what do I mean with lightweight dependencies? If you work with AWS Lambda and you work with the SDK, you usually get clients that come from the SDK, so a client for DynamoDB in this case. And that client will actually look at your class path and try and figure out what kind of HTTP clients do I have available to make this connection to DynamoDB. And by default, I think it brings Netty, and you can or Apache HTTP client, and you can exclude those because AWS also provides a very lightweight HTTP client called the URL connection client. And this URL connection client is very lightweight compared to Netty because it's not using any reflection. It's very fast, very straightforward. If you would move native, they also have like a more native, so a custom runtime client, which also shaves off another couple of, I would say, 80 to 120 milliseconds of your initial setup. So very useful if you have like very low latency requirements with very fast starts. Try and move towards these very lightweight dependencies. Number 4, pre-configuration. So Lambda is pretty smart, and Java is pretty smart, and the SDK is really smart. It can do a lot of lookups. It can find things from your environment from the class path. But if you let it do so, it will consume quite some time during the initial start. So in this case, if you know where your function is going to run, specify it explicitly, so it doesn't need to look up in the environment where it is. It will just make it more performant. So specify the region, specify that it can find the credentials to connect to a remote service like DynamoDB from the environment, specify a specific HTTP client, specify the endpoint. If you don't specify the endpoint, the SDK will look in the internal JSON file, try to parse that entire file to figure out what the endpoint for your region is. So in this case, also with specifying these things, you can shave off another like 50 to 60 milliseconds. If you want a big improvement, or first big improvement, is use tiered compilation. Anybody know what that is? Heard about it? Read last month's Java magazine? No? I see some hands there. So tiered compilation in the JVM. If you have a Java process and the JVM starts, it looks at your code and it will go through a couple of steps. So from the bottom to the top, and it will try to increase like the optimization of the code and the code path and its execution path. And what you can do with tiered compilation is also after the first phase, so after the level 1, you can stop the compilation because it will increase the performance, especially for very short running functions. This can be very beneficial. You can do that really quickly also with your own applications if you want to, because it's just a very simple setting on the JVM where you say, I want to use this tiered compilation and I want to stop after the first iteration. So stop profiling for more optimizations because I want to have a faster start. And what we used to have in the JVM is like a client and server mode. I'm not sure if you are aware of that. But in essence, with tiered compilation was a replacement for the client mode that you could provide to the JVM, because that would always start a bit faster, and the server mode would opt for more optimization. So, tiered compilation. Just to give you an example of the difference, there's a very simple chart. So you see the default JVM settings, so without specifying tiered compilation. In this case, where we see a cold start with, let's say, a 90 percentile of 5 seconds, and with the tiered compilation, it's like 2 seconds. So it can really shave off quite some seconds from your startup. Number 6, proficient concurrency. So if you work with AWS Lambda, it's very known, like serverless functions are known for starting with 0 and scaling up really quickly. If you have slow functions, you can let AWS or the cloud provider pre-warm your function so it's in a ready state to accept requests. And that's what you can do with proficient concurrency. So Lambda is based on an event, so you send an event and the function triggers. The more events you send, if they take a specific period in time, the more functions it will start. So if we talk about concurrency, the number of parallel functions that are running to serve your load, you can provision that. So we already mentioned like the Lambda initialization and the cold start. With proficient concurrency, you can let the first 3 steps be taken care of before your function actually starts to serve its traffic or work its magic. This will save you quite some time, especially for some Java functions which have a very high cold start. Also with AWS CDK, which is like a Java library for doing infrastructure as code, it's very simple to set up. Just specify like the amount of warm functions you want to have, but it also supports like auto-scaling. You can do this either on demand or on the schedule. So in this case, it will scale up the proficient concurrency, so the warm functions to prepare, for instance, for a very predictable load. Let's say everybody starts using your app in the morning at 9 a.m. You can scale it up just before that, and when during lunch you need to scale it down, you can do so. But you can also use this based on a metric. So you can actually take a look at how many functions are running, if they're all being utilized, and if they're not being utilized, you can either scale down, or if you see that they're all utilized, you can aggressively start to scale up. So you can do that also with auto-scaling, and do that based on the metric, so for instance, based on the utilization. Number 7 improvement, frameworks. So I come from a very long Java background, used to build a lot of applications with Spring, and especially if you start looking at Java and Spring in the cloud, it's not a match made in heaven, or at least not right now. I think with the new Spring release and Spring Boot release, it gets a lot better because it supports native. But there are many frameworks that talk about cloud-native serverless Java functions. So Quarkus, Micronaut, Spring Boot. And if you look at, for instance, Quarkus and Micronaut, they use almost no or almost no reflection. And reflection is very costly in a serverless environment because it's very time-consuming. So they do a lot of like ahead-of-time compilation or dependency injection at compile time, which makes it a lot faster because you will do it while you're compiling it and not while you're running it. So that will also help a lot. But I think, and this is also sometimes an elephant in the room, also don't use a framework. Will save you lots of cold start time. And this can, for instance, reach up to like 45% of the cold start time of your application, because those frameworks add quite some weight to your function. Package size, number 9. So the bigger your application, the more dependent jars, the bigger the file. And we already mentioned, when your function starts, it will download your code. So the bigger the jar, the slower it gets. Same with containers. The bigger the container image, the slower it gets to download the container image to run it. But also to execute it. So libraries, class path scanning, everything can add up. Number 10, GraalVM. I guess everybody knows GraalVM in the meantime. So ahead-of-time compilation to a native image. If you have a very simple function, for instance, in this case, it's a very simple function that listens to a request coming from an API gateway. It just logs it and sends back a 200. If you use GraalVM and do this ahead-of-time compilation for your function and create it into a native image, this is, for instance, the performance figures that you can see. So Java 11 in a cold start with like 2 GB of memory will have like an initializing phase of about 420 milliseconds. If you would create that same function and create a native image out of it with GraalVM, you would need a lot less memory, and you will gain a lot more performance. So very interesting technology to use if you go serverless with your Java applications. Number 11, Crack. Anybody who knows what that is? Yeah, I see a couple of hands. For those of you who are, for instance, at JSpring, there's a very nice talk from JSpring from, I think, last June by, I think, Simon Ritter. It's a new feature in the, well, I'm not sure if it's a really new feature, but it is something which is part of the OpenJDK, currently in an experimental phase. And what it does, it executes your function, lets it run, tries to optimize, and create a snapshot out of it. And based on that snapshot, you can then again start the JVM with that snapshot. So you can do all the pre-optimizations, pre-compilations to make it really fast in like a cloud environment. Very interesting technology to take a look at. It has some downsides also, but I don't have time for that right now. Very easy one, 12. As Java programmers, we just saw a talk like about threads and parallelize. So if you build an application, I worked with this team recently. They built this importer function, and it was running against like the function timeout. And it was running against that timeout because they were doing big import jobs. And but those import jobs were they were being handled sequentially. And like we mentioned, if you give the function and the JVM more memory, you will get more CPUs. You can use parallelization. So very simple thing to keep an eye on. Leverage those virtual CPUs. Number 13, switch to ARM. So different CPU technology is very useful. I tried it a couple of times. It's very useful if you have like multiple threads, lots of I/O. It will give you quite some performance. So very interesting to take a look at. I'm almost there. Number 14, be very careful with layers. So if you use Lambda functions, you can provide like generic functionality in a layer. Sometimes these layers, they just like in a container, they get staked up into your function as a file system, and you can use those libraries. But also sometimes on these layers, on these functionalities that you add to your Lambda function, they can add quite some latency. So this is an example of a graph that I used for a recent function. I tried to use OpenTelemetry, and they have an extension or a layer for that, so you can add like a collector to your Lambda function that will actually send out your traces and your information. It was very slow, as you can see. It's almost like about almost 5 seconds for cold starts. And after I removed that and just went to plain X-ray, it went more than half in performance, or it was like 200% gain for performance. So I'm almost out of time. So overall impact, because I went through quite some. AWS also has this very interesting workshop for Java and AWS Lambda, and especially if you're a Spring Boot developer and you want to migrate away from Spring Boot, like from a serverful to a serverless structure, they've written down this entire workshop where you can take all these different steps. You can see like the percentage of improvement that you will get. So if you look at the top for a Spring Boot application, what you would normally have with like 2 GB of RAM, you would have like a P95, 95 percentile of start time, about I think, what is it, 13 seconds. If you move all these different steps and you apply all of them, you can end up eventually at below a second. So I think that's it's very decent performance. And there's lots of things to do, and there's still lots of things to explore. Thank you very much.